Hey, welcome back to this 4.5. We're going to be solving non-homogeneous differential equations now. So we want to reintroduce some of the notation we used before. So first factoring, and we're working with the operators, the differential operators. So you may or may not have remembered that we can always rewrite derivatives using big D, this big D notation. So for example, if you have the third derivative of y with respect to x, you could rewrite that as d3 of y. Okay, so we want to then rewrite our differential equations with this notation. So recall these guys, these homogeneous differential equations, linear constant coefficients, y double prime plus 4y prime plus 4y equals 0. I want to rewrite that. And then I'm going to use the operators and we're going to factor them. Okay, so I could rewrite y double prime as kind of doing d twice plus 4, then I'm doing one derivative plus 4. And you think of that thing as a polynomial operator on the function y. You can then factor that thing, that polynomial operator, into, looks like d plus 2, d plus 2. And that is equivalent to the original differential equation. So we'll need to work with that kind of here in our exploration. Okay, we want to now introduce the idea of an annihilator. So an annihilator is basically a polynomial operator that makes a function equal to 0. And you probably kind of have been introduced to this back in Calc 1 and Calc 2. So recall, if you have like a polynomial, we'll just say y equals 3x cubed. If you keep taking the derivative, eventually you'll get 0. 9x squared, 18x, 18, 0. Okay. So basically, if you're given a differential equation like d4 of y equals 0, or in other words, the fourth derivative of y equals 0, you kind of know that the solution has to be some sort of polynomial like 3x cubed. Okay? I don't know. But what we're looking for in general are ways of kind of annihilating functions. How can I take a derivative of it in a weird sort of way that causes it to be 0? If you think about it, that's all we've been doing up to this point. Like in the previous chapter, 4.3, that's all we did with these homogeneous differential equations, right? So also then recall 4.3 stuff, things like y double prime minus y prime minus 6y equals 0, this thing. We could rewrite it with our differential operator notation, d2 minus d minus 6 of y equals 0. And I claim that if you can figure out the solution, this thing right here is the annihilator of it. Because if you plug that solution into this differential equation, you get 0, right? So anyways, let's see if we can factor this, right? So that's d minus 3, and then I think d plus 2 of y equals 0. So the solution of this thing, if you remember doing your characteristic equation, is 3m equals -2, and then y will be c1 e to the 3x plus c2 e to the -2x. This stuff here will annihilate those exponential expressions. And in fact, this part of it right here will annihilate this part right here, and the other part will annihilate the e to the 3x. So you know, what am I trying to do again? What the heck is going on? What is happening? I'm looking for a way to take the derivative of functions that I'm familiar with, like the exponentials, the trig functions, the polynomials, and I'm trying to find ways to take their derivatives to make them equal 0. Okay. So what is happening? I'm trying to take derivatives of functions in a way that makes the function, or that transforms a function into 0. Okay, so taking that thing I just put in red there, let's take a look at that. D plus 2, and let's just plug in the e to the negative 2x there. So I'll have d of e to the negative 2x plus 2 times e to the negative 2x. The derivative of e to the negative 2x is just going to be negative 2, then e to the negative 2x, and then plus the 2e to the negative 2x, and that'll equal 0. So what I have there is an annihilator of e to the negative 2x. And in general, I can annihilate any exponential function just by using a d plus or minus m, depending on what your exponent is. So in general, I can annihilate a function. F of x, we'll say, equals c e to the mx by using d plus or d minus m, right? Minus m as the annihilator. It's a polynomial operator that works on this function e to the negative 2x to make it equal 0. And of course we could show that right here. You have the derivative e to the mx. And there's a c in there. Okay, so the derivative of that thing, c e to the mx minus m times c e to the mx. The derivative of the first part is c e to the mx times m. So you get m c e to the mx. And that'll be minus m c e to the mx. And of course that will be 0. Okay. So I guess it's kind of crazy the way it worked out. What we've been doing with the homogeneous equations is kind of studying annihilators. It's kind of figuring out ways to cause exponentials to be 0, cause trig functions to be 0, and cause polynomials to equal 0. Okay, so let's make this a little more standard, standardize it a little bit more. First, let's note the polynomial annihilators. And we kind of already have that from our work above in Calc 1. Basically, if you have a polynomial of degree 3, you just have to use an annihilator with a degree that's 1 more. Okay, so this kind of gives us our general form for it. If you have some function y equals x to the n, its annihilator will be n plus 1, right? So d to the n plus 1 of y will equal 0, because you're going to be taking the derivative of it n plus 1 times. Here for 3x cubed, I need to take the fourth derivative to make it be 0. Okay, so the notation we'll kind of use is for, if you remember polynomial operators, then we would write L for the polynomial operator. So L of y would be kind of, instead of writing d squared plus d plus 1 of y. Okay, so this L thing is basically this thing as you read through in the book. Okay, so what we're doing is looking to annihilate some polynomial x to the n, some variation of that, and in order to do that we need to take its n plus first derivative. X just to the n, and that will equal 0. Okay. All right, so the second type of annihilator that I was kind of just introducing there is the exponential annihilator. And that operator, and we're going to be applying it to things not just of the form e to the mx, but also with x's in front of it. Okay, so we'll have multiple root issues, like when we were dealing with in 4.3, where you'd have multiple repeated root problems. In the repeated root problems, you always have to tack in an x. So we also want to annihilate the x part of it, whatever that may be. So let's write x to the n times e to the mx. To annihilate an object like that, we have to go d minus the exponent m, and then depending on the number of repeated roots, we have to keep on applying the differential operator. So it'll turn out you could just put this to the n plus 1, and then applying that to this expression, you'll get 0. Okay, the third type we care about are the trig annihilators. And in those cases, we want to annihilate things of the form x to the n, e to the, let's use alpha x, cosine beta x plus x to the n, e to the alpha x sine beta x. So again, allowing for repeated roots. And the formula will then be, the polynomial operator will be d squared minus 2 alpha d plus alpha squared plus beta squared. But in practice, I'm not going to kind of have that memorized. Generally, I can recover the annihilator from the form of the thing we want to annihilate, basically. So I would be applying it to, again, this x to the n, e to the alpha x, cosine beta x plus x to the n, e to the alpha x, sine beta x. And in that case, you would get 0 popping up. Okay. But the form of the operators, they just follow what we did in 4.3. So if you kind of know the solution to the differential equations, the homogeneous types, then you kind of know which annihilator you're going to have to put forth. Okay, so anyways, let's look at some of the intro exercises here to see if they're manageable. 4.5-ish. Okay, so write the given differential equation in the form L of y equals g of x, where L is the linear differential operator with constant coefficients, possible factor L. Okay, so this first problem is basically what I was doing here in my first section, factoring operators. So problem 1, let's take a look-see. I want to rewrite it using the differential operator. Okay, so 4y double prime minus 16y equals sine of x. Okay, so I just replaced the y double prime with d squared, and then minus 16, and that will act on y, and the output will be sine x. So this, you notice, is a non-homogeneous differential equation. This is what we're hoping to solve in this section. You can factor out the 4, so you want to completely factor this. D squared minus 4 of y equals sine x. And then I can factor the d squared minus 4 and the d minus 2d plus 2. Okay. So hopefully not a big deal. And that's all you're doing in these first couple. Okay, once you get beyond that, then you're going to start finding annihilators for particular functions. And these will just follow from the rules for the annihilators. It's at point A, B, and C. Okay, so let's go through these guys. Number 6, I want to find an annihilator for 1 plus 5x minus 3x cubed. And basically, you just go d and 1 power higher than the polynomial. So d plus 1 is to the 4th. And you note if you applied this to the 1 plus 5x minus 3x cubed, it would equal 0, right? Because if you do the derivative once, you're going to get 5 minus 9x squared. Do the derivative twice, you'll end up with negative 18x. Do the derivative another time, you get negative 18. And then finally, the derivative of that will be 0. Number 7, we have 1 plus 3e to the 7x. So you have to work with the components, the terms of this expression. So I'm going to need an annihilator for the 1, which is basically just d. Okay? So I need that. And then I need an annihilator for this 3e to the 7x. Okay? And the annihilator for that is just going to be d minus 7. Okay, so for exponentials, you don't have to worry about the constant in front. It's just solely dependent on the exponent. So it'll be d minus 7. Okay. Let's look at number 8. Here we have cosine of 4x. So for cosine of 4x, if you think about it as a solution to a differential equation, what would be the scenario in that case? Basically, the roots of your characteristic equation must have been 0 plus or minus 4i. Okay, so your differential equation, kind of back engineering the characteristic equation, must have been 4m squared. And I mean, you could literally kind of write it out in terms of m. So it must have been m plus 4i times m minus 4i equals 0. And then you can multiply it all out. So foiling, so you get m squared plus 4im minus 4im, and then minus 16i squared. 0, and then you get m squared, these guys cancel, minus 16i squared. I squared is negative 1. So you get m squared plus 16 equals 0. And that thing is your annihilator, because your differential equation, if you back engineered that, would just be y, the second derivative of y plus 16y equals 0. Okay? And so your annihilator is d squared plus 16. So you can always back engineer it. You can even back engineer number 7, right? So here the roots of your characteristic equation must have been 0 and then 7, right? So you could rebuild it. It would be m times m minus 7 equals 0. In other words, m squared minus 7m equals 0. So that must have come from the differential equation y double prime minus 7y equals 0. And then in the differential operator notation, that would be d2 minus, sorry, this should be y prime. So d2 minus 7d of y equals 0. And of course, if you were to factor that, you would just get this thing right here, right? So as far as memorization goes, if you kind of already know how things work, you already know how to annihilate these functions. So let's do another one. So number 9, I have 14x plus 10x squared minus 7 sine to the sine of 6x. Okay. So again, if you want to, you can go and take a look at the roots, right? So you would have to have m equals, this guy is from a repeated root of 0, right? So it'd be 0, 0, and then this guy is from the root 0 plus or minus 6i, right? So you can then back engineer. You can say it must have been m squared times m squared plus root 6, right? Or rather, geez, what is it going to be? Well, we can always write it out, right? M plus 6i, so it's going to be m squared plus 36, m minus 6i. If you were to FOIL that out, you would get m squared plus 36. And so our annihilator is basically sitting right there. Actually, you need another 0, right? So the first would give you c, and then the second one would give you cx, and the third one would be cx squared. So this should actually be m cubed. So our annihilator for that would be d cubed times d squared plus 36. And if you follow the formulas that I gave you, you're going to get the same thing, right? And I was saying earlier, you know, it's not necessarily the kind of you don't necessarily have to memorize that. You can always kind of recover it if you just remember the process for the characteristic equation, finding those, finding the m values, and kind of just back engineering it. You can get the annihilators through back engineering, right? So here this was d squared plus 16. Okay. Here, yeah, this would give you that. Let's try this next guy, number 10. I have e to the negative x plus 9x e to the, is that positive x? Yeah, and then minus x squared e to the x. Okay, so our roots must have been -1, and then this was from a repeat. So I need 1 for the original and then 1 for the repeat, and then another 1 for the x squared. Okay, and again, the coefficients don't really matter. So I would have had m plus 1 for the -1 times m minus 1 for the 1s, and then that would have been cubed. Okay. So then the annihilator should be d plus 1 times d minus 1 cubed. Okay. Let's try the next guy. So number 11, I have 8 plus e to the x cosine 5x. And to annihilate it, so the first guy I need a d, right? And then the second guy for this part, if you think about then in terms of the solutions, the first number 8 is just a constant, so that would have been from a root 0. The second part is from the root 1 plus or minus 5i. Okay, so to get the annihilator from that, you know, you can literally just sit there and memorize that formula. See, alpha is 1 and beta is 5. But what I suggest is just recovering it, doing your multiplication. So you would normally have m times m minus 1 plus 5i, and then m minus 1 minus 5i, and then just FOIL that out, and it'll give you the annihilator that you would have gotten through memorizing that d squared minus 2 alpha d, which you may want to memorize instead. I don't know. It's up to you. But I just do it this way. So I'd have m squared. The first, the outer is going to be minus m times 1 minus 5i. The inner is going to be minus m times 1 plus 5i. And then the last is going to be plus 1 minus 5i times 1 plus 5i. So I'll have to FOIL that. It's a little bit of work, but personally it's easier than memorizing things for me. So I have m squared minus m plus 5im minus m minus 5im plus FOILing that last part. The middle terms cancel, so you just get 1 minus 25i squared, which will be 1 plus 25. And then, so what does that equal? The m's, so we get m times m squared minus 2m. These cancel, and then plus 26. So your annihilator would be d times d squared minus 2d plus 26. Okay, so that gets you through at least those first integral problems. Now we actually want to use this method to solve these non-homogeneous differential equations. Okay, so section 3 then, actually solving these guys, L of y equals g of x by this method. So first, what we're going to do is solve the homogeneous version. So solve L of y equals 0. And what you end up finding is the complementary part of the solution. So remember, these solutions will always have the form y equals y sub c, the solution to the homogeneous part, plus y sub p. And our main goal is to find y of p. Okay, but if you solve L of y equals 0, that's going to give you y of c, okay? Y sub c, the complementary part. Okay, so once you solve that, then you're going to find the annihilator of the g of x and apply that to the original differential equation. So you'll be applying some operator to this L of y thing, and what will happen there is it will turn it into another homogeneous differential equation, and then you can use your answers from 1 and 2 to find the abstract form of y sub p. Okay, so use 1, 2 to find y sub p, and then you'll use the method of matching coefficients to solve basically, and then finally the solution y equals y sub c plus y sub p. Okay. Once we get in there and we do it a couple times, hopefully it won't be too bad, but I'm going to warn you right now, these problems typically take me a page or two. Okay? Every time I do one, it at least takes me a whole page. I do not write my work like you normally would. I lay my paper sideways and work on the top down. Okay, so anyways, let's dive right in and see what we're dealing with. So number 12, we have y double prime minus 16y equals 96. Okay, so this one should be fairly simple to start with. Let's give it some room. Okay, so first I want to solve the associated homogeneous differential equation y minus 16y equals 0. I know how to do that from the previous section, right? Get the characteristic equation, m squared minus 16 is 0, so this would be m minus 4, m plus 4 is 0, so m is 4, m is negative 4, and then my complementary part of the solution will be y sub c equals c1 e to the 4x plus c2 e to the negative 4x. Okay? So that will be part of your solution. Okay, now I want to go back to the original equation here and rewrite it as a differential operator. So I'd have d squared minus 16 equals 96. And then I want to annihilate the right side. So I'm going to apply an annihilator to both sides that will get rid of 96. And of course, to get 96, to take its derivative and get it equal to 0, all you have to do is take its derivative, right? So just apply d to both sides. And there should be a y in there. There should be a little y sitting here. Sorry. So if you apply d to 96, the derivative of 96 is 0. So you always want to turn the original differential equation, this non-homogeneous, into a homogeneous, okay, using the annihilator. Okay, once you get this thing, then it's going back to business as usual. You get the characteristic equation and then solve it. Okay, so in this case, then you need not really convert it back. If you convert it back, you're kind of, I mean, back where you started. If you want to, you can, but okay. So let me show what happens when you kind of convert it back. You're going to get d cubed minus 16d applied to y equals 0. This would then be d cubed y minus 16 dy equals 0. That would be y cubed minus 16 y prime equals 0. And then you get your characteristic m cubed minus 16m equals 0. And then you factor it into m times m squared minus 16 equals 0. But what I'm saying is you could literally just cut all that out. Look. Just replace the d's with m and drop the y. And you have your characteristic equation there. It's already factored, kind of. I still have to factor the m minus m squared minus 16, but you kind of already did that actually over here, right? So you would have m times m minus 4 times m plus 4 equals 0. Then our roots of that thing would be 0, 4, and negative 4. So the solution of this new differential equation, this homogeneous guy, is going to be the 0 just gives you a constant, plus c2 e to the 4x, and then plus c3 e to the negative 4x. Okay. So to find y sub p, now what you do is compare and contrast y sub c to this guy. Okay, so you kind of compare this to this. Okay. So in this new function that I have, y, I note that y of c is sitting right here. Okay, so this is y sub c. So the particular part of my solution is just that first part. Y sub p is this. Okay, so I'm going to rewrite it. Y, instead of using constant c1, c2, I'm just going to use a, b, c, d, e. So this will be y equals a. And that will be my particular part. Okay, I need to figure out what a is. To figure out what a is, basically you're just going to plop it back into the original differential equation. Okay? In order to do that, I need to have up to the second derivative. Okay? So now I take all of this material, maybe put it in yellow. I need to take all of this junk and plop it back into this guy here. And then I should be able to figure out what the heck a equals. Okay, so if I plug that information in there, I'll have 0 minus 16 times a equals 96. And then I could solve for a. Right? So I'd have negative 16a equals 96. Divide both sides by negative 16. I get negative. Calculator. It's too early for this. 16 divided by 16. 96 is 1/6. So it's negative 1/6. So my final solution then is y sub p plus y sub c. So my solution is y equals y sub c, which is c1 e to the 4x plus c2 e to the negative 4x plus y sub p, which is minus 1/6. Okay. Barring any solutions, of course, I misdivided. So 96 divided by negative 16 is actually negative 6. If you get really hard up on one of these problems, you can send me an email and I can tell you what the solution is, as long as you're not doing it to me on every problem. Because, I mean, I get it. It's a lot of work, and if you make one little mistake, I mean, it's going to force you to be more on your game with regards to being organized. And some of you, I can tell, are really already good at this. But you know, as the problems get longer and longer and longer, there's only so much organization that you can do, and you'll be looking for little mistakes all over the place. And you could have 3, 4 little mistakes. So if you want to, you can always send me an email, and I will gladly send you the answer, just in case you're thinking, well, I must have made a mistake here. I trust you enough that you're not going to cheat and take advantage of that. Okay, let's look at another guy, something else, right? So let's look at number 15. We have y triple prime plus y double prime equals, well, let's not do one that's a polynomial. Well, okay, let's go ahead and do this. It's 7x squared. Okay. First, get the homogeneous version. 3 plus y double prime is 0, so m cubed plus m squared is 0. Factor out the m squared, so you get m plus 1 is 0. So the roots 0, 0, -1. Okay. So our particular solution, or sorry, our y sub c, the complementary part, is going to be c1 plus c2x plus c3e to the negative x. Okay, then I got to rewrite the original with annihilators. So the original is d3 plus d2 of y equals 7x squared. To annihilate 7x squared, I need d3. So I'm going to have to apply a d3 on the outside of this. Factoring a little bit, I get d3 times d2 times d plus 1 of y is 0. So I get d5 times d plus 1 of y equals 0. So my roots, if you just pretend the d's are m's, basically you get 0, 0, 0, 0, 0, -1. So our solution from this part, I'll just call y, would be c1 plus c2x plus c3x squared plus c4x cubed plus c5x to the 4th plus c6e to negative x, right? The part I want then is everything except that yc part. So yc, taking that away, I'll have this part of it as my particular form, right? So y sub p is going to be, and I already placed the constants with a, b, c, ax squared plus bx cubed plus cx to the 4th. Then I think about my original differential equation back here. I'm going to need a third derivative, so yp prime is 2ax plus 3bx squared plus 4cx cubed. Yp double prime is 2a plus 6bx plus 12cx squared. Yp triple prime is going to be 6b plus 24 cx. Okay, then I take all of this jazz and I plop it into the original differential equation here. So I get 6b plus 24cx plus y double prime, 2a plus 6bx plus 12cx squared equals 7x squared. And then you equate coefficients on the terms, okay? So if you want to, you can kind of collect stuff. After a while, you'll be like, no, I'm doing enough work, thank you. But just for illustration purposes, get the x squared by itself, get the x parts by themselves. So you would have 24c plus 6bx, and then get the constant parts by themselves. So plus 6b plus 2a. And on the other side, you have 7x squared, but technically you also have plus 0x and then plus 0. And then you equate the coefficients. Okay, so the coefficient of x squared over here should equal the coefficient of x squared over here. So I get 12c equals 7, and I can automatically solve for c. Then the coefficient over here should equal the coefficient of x over here. So I get 24c plus 6b equals 0. And then finally, the coefficient here should equal the coefficient here. Constants equal each other. 6b plus 2a equals 0. And then you have a system of equations, 3 unknowns that you should be able to solve. Okay. Okay, so first I'm going to kind of plop this into here. 24 times 7 over 12. It's a little bit like solving partial fraction, those partial fraction problems in Calc 2. 12 goes on 24 2 times, so we get 14 plus 6b equals 0. 6b equals negative 14, so b equals negative 7 over 3. And then plop that into here, so 6 times negative 7 over 3 plus 2a equals 0. So 3 goes into 6, 2 times negative 14 plus 2a equals 0, so 2a is 14, so a is 7. And then I can plop that back into my solution form here. So y will equal y sub c, which is c1 plus c2 x plus c3 e to the negative x plus y sub p with a, b, and c filled in, right? So a is 7, so plus 7x squared. B is negative 7/3, so minus 7/3 x cubed. And then c is 7/12, so plus 7/12 x to the 4th. And then you say a prayer and plop it into the WebAssign, and hopefully you have the right answer. In this case, I do. Okay. Let me try number 16, I guess. They get harder and harder as you go. They can be quite annoying, especially if you don't get the answer. And some of these have some pretty nasty fractions involved. Let's look at number 16, I guess. So I have y double prime minus y prime minus 20y equals e to the 5x. Oops, I stepped on my cat. Sorry, buddy. Stack of papers. I'm just worried of making a little mistake in that case. Anyways, so get the get the homogeneous version set up with the characteristic equation would be m2 minus m minus 20 0, so m minus 5, m plus 4 is 0, so m is 5 and negative 4, so the complementary part is going to be c1 e to the 5x plus c2 e to the negative 4x. Then go to your annihilator. So originally d2, and I mean, you don't even have to write it like that, right? You could just use the factored form from here. So it's going to be d minus 5 times d plus 4 times of y. To annihilate e to the 5x, you need d minus 5. Okay, so equals 0. So I have d minus 5. I mean, we could just go to our characteristic equation then. So m minus 5 times m minus 5 times m plus 4 is 0. So our guys are 5, 5, and negative 4. So our solution to this new differential equation c1 e to the 5x plus c2 x e to the 5x plus c3 e to the negative 4x. So the particular part is just this part, comparing it then with the complementary part, because this part and this part are in the complementary solution, so we throw those out. So our particular solution will have the form c, well, let's replace c with an a. We can erase it, that would be great. There we go. So I have ax e to the 5x, and then I need up to the second derivative. And this is where it can get kind of annoying, right? So you have 5, taking the derivative e to the 5x is 5e to the 5x. I'm leaving x alone. I have to do a product rule. And then you just have ae to the 5x, second derivative. So I have 25 ax e to the 5x, product rule, plus 5ae to the 5x, plus the derivative of this part is 5ae to the 5x. Simplify it first. Right? So these two terms are the same, so I get 25ax e to the 5x plus 10ae to the 5x. Then you plop it back into the original differential equation. So you'll have 25ax e to the 5x plus 10ae to the 5x minus y prime, which should be 5ax e to the 5x minus ae to the 5x minus 20 times y, so that would be minus 20ax e to the 5x, and that should equal e to the 5x. Okay. Again, you play this game of equating coefficients. Let's simplify if we can first, right? So we have 25 of these minus 5 of those minus another 20 of those is just 0. So that goes away nicely. We have 10 of these minus 1 of those being 9a e to the 5x equals e to the 5x. And then equate coefficients. The coefficient on the right is just 1. So you have the coefficient on the left, 9a, equaling 1. In other words, a equals 1 over 9. In other words, our particular solution, substituting in now, is going to be 1 over 9 x e to the 5x, and then our solution to the non-homogeneous equation, just add that into y sub c, right? So y would equal c1 e to the 5x plus c2 e to the negative 4x plus 1/9 x e to the 5x, like that. Yay. And then say your prayers and plop it into the system. Let's see if we can find one that's nastier. Let's try this number 19, see if that's anything worth worrying about. We have y double prime minus 2y prime plus 37y equals e to the x sine x. Okay. So first off, looks like the characteristic equation here ain't going to have real roots. I don't know. So m is negative 2 is 2 plus or minus the square root of b squared, which is 4 minus 4 times a times c, all over 2 times a. So you get 2 plus or minus the square root of 4 minus 4 times 37. Or you could think of it as 1 4 minus 37 4s, which would be negative 36 4s over 2. And then you'd have 6 squared times 2 squared, which would be 12 squared. So that's square root of 12 squared is 12. So you get 2 plus or minus 12i all over 2. And that would be 1 plus or minus 6i for your solution. So the complementary part, e to the 1x times c1 cosine 6x plus c2 sine 6x. And you should see that in your solution in my solution over here on the right, and certainly you do. Just want to make sure I'm on target before going. Okay, so form the other part then. So it looks like we have d squared minus 2d plus 37 of y. I want to annihilate the e to the x sine x. So to do that, that would normally have the root, if you are, this thing would be the solution to the differential equation, which would have a characteristic equation, which would have roots 1 plus or minus I, right? So the characteristic equation would be something like m minus 1 plus I times m minus 1 minus I. Foiling that junk, you would get m squared, the outer, minus m times 1 minus I, minus m times 1 plus I, plus 1 plus I times 1 minus I. And then that would be m squared minus mi plus m, minus m plus mi minus m minus mi plus 1 minus I squared, which would be plus 1. So you'd end up with m squared minus 2m plus 2. So the annihilator is d squared minus 2d plus 2. Okay, and then that would equal 0. Then the solutions of this thing, the roots, the characteristic equation of that would be this, you would have roots m equals, and you're kind of doing some redundancy, right? But you need to do this, okay? Because it won't always be so easy. So just follow the program I've laid out for you. Don't overthink it. Okay, so the roots from this part we already have are 1 plus or minus I. The roots from this part then are the 1 plus or minus 6I. And then our particular solution, or sorry, we're not at the particular yet. The solution of this guy is e to the x times c1 cosine x plus c2 sine x. And that's going to be the particular part there, plus e to the x times c1 cosine 6x plus c2 sine 6x, right? So the particular part is all of this junk, okay? So y sub p is going to be, and I'm going to distribute in the e to the x, replace the c's with a and b. I get a e to the x cosine x plus b e to the x sine x. And then for my differential equation, I'm going to need the second derivative. So y prime is going to be, and I have to do a product rule. So take the derivative of e to the x first. That's just e to the x. Take the derivative of cosine next. It's going to give me negative sine. And then the second part, take the derivative of e to the x first. So b e to the x sine x. Then the derivative of sine x. It's just cosine x. Not done yet. Second derivative then. Can I do any simplifying? No, not really. You can kind of do some if you're willing to combine coefficients like a plus b, e to, but I'm not even going to bother. You know, I don't think it's going to be worth the work. I'm just going to brute force it. Okay, okay, so I'll have, working with that, I need two terms. So I'd have leaving e to the x along, or taking the derivative of e to the x first, I have a e to the x cosine x, and then minus a e to the x sine x, and then the derivative of this, e to the x first, so minus a e to the x sine x, take the derivative of sine x, so minus a e to the x cosine x, plus the derivative of this, b e to the x first, sine x, plus b e to the x cosine x, and the derivative of that, plus b e to the x, derivative of e to the x first, cosine x, minus b e to the x sine x, and you hope you can simplify that, probably not, maybe. So we have a e to the x cosine x minus a e to the x cosine x, those are gone. I'll have then 1, 2 of these, so minus 2a e to the x sine x's. And then b e to the x sine x minus b e to the x sine x, those are gone. And then I'll have plus 2b e to the x cosine x. And now I'm plopping all of that into the original differential equation, which was way back here. Okay? So first starting, and one way I kind of do this is just to work in-house, so to speak. So I'm going to kind of just add them up like this. So I have the y double prime, and then I need to go minus, let me put it in a different color, minus 2 of these, and then plus 37 of these, okay? And then just add them up column-wise, and then do my equation like that. Okay? So it's better than having to rewrite it. Anyways, let's see what we get, right? So I have a negative 2a e to the x sine x right here. I'll have a negative 2a e to the x cosine. This will be positive 2a e to the x once I distribute, because I have to distribute these terms. So that thing, that positive 2a e to the x sine x, is going to cancel with this negative 2a e to the x sine x. Okay. Then distributing here, I get negative 2b e to the x sine x. There's not another one of those floating around, is there? There is, but I'm going to hold off on it, right? There's a plus 37 right here. If you want to, you can go and do it. That'd be 35 e to the x sine x's. Okay, so anyways, how about the b e to the x cosine x? There's one here, and then I'll distribute this negative 2, so it'll be negative 2 there. In other words, these will just be 0 when I add them up. And then I have whatever's left over from that first part. Okay, it's really dangerous doing that, but it does save your hand a little bit of trouble if you're old and you're getting carpal tunnel at this point like me. But you got to be super careful, right? Because it's super easy to make mistakes. It's just so easy. So anyways, it looks like I'm getting a 37, you know, because, all right, so what do we have? It was this guy, and I'm already scared that I screwed something up. It's just, sometimes it's better just to write it all out, I swear. Let me kind of go through this again. So negative 2a e to the x, I'm saying, is canceling with this. The 2b e to the x is going to cancel with this, negative 2b e to the x. Ooh. Okay, and then I have these 4 that kind of cancel into each other. So 37a e to the x minus 2a e to the x. Those are both cosine x versions, so I get 35 of those. So 35, and I lost my b on the first guy, I think. 35a e to the x cosine x, and you know, plus the 37 minus the 2, so 35b e to the x sine x, and I'm okay, right? Right, so that all equals e to the sine x, e to the x sine x, right? Okay, so you're looking for terms e to the x sine x on both sides, right? So there's an e to the x sine x, there's an e to the x sine x. The coefficient on the right is just 1, right? So on the left, I have 35b e to the x sine x. On the right, I have 1 e to the x sine x. So b is equal to 1 over 35. And then I'm looking for the e to the x cosine x's. And on the right, there isn't one, right? You could put 0 e to the x cosine x's if you wanted to, and then you could equate their coefficients. So you would have 35a equaling 0. In other words, a is just 0. Okay. Sorry, I had that blue. Okay, so the particular solution y sub p, then the first part of it is just 0, and then plus 135 e to the x sine x. And then we want to add that into the complementary solution, which is sitting over here, and that would be our answer. Okay, so our answer, y equals e to the x times c1 cosine 6x plus c2 sine 6x plus 1/35 e to the x sine x. And as usual, you cross your fingers, whatever you do for luck, and hope it's right. Okay, so I'm not lying to you. These can be quite annoying. There's some initial value problems once you get towards the end there. Let me try number 23, because that looks kind of annoying, and then I'll call it quits. So as promised, send me an email if you want a solution to the problem you're working on. Please don't take advantage of that. I didn't spend 10 years in college just so I could look up answers for my students. Please don't do that to me. But every once in a while, here and there, preferably if you have a set of them you can send to me, then I can send you the answers. But okay. Whoops, wrong one. I want to do 23. That was 22. That one actually looks easy. Well, relatively easy. Y double prime plus y equals 8 cosine 2x minus 4 sine of x. Y of pi over 2 is -1. Y prime of pi over 2 equals 0. Okay. You gotta be real careful. Even my handwriting, I found that my y's look like 4s sometimes. That any little thing like that, like I would, okay, I'm gonna shut up. Just if you're sloppy, those little sloppy errors are going to accumulate as you go through these problems as they get bigger and bigger. So I'm always an advocate of having very organized work. I appreciate that in my students. I just want to say how good that is. Okay, so if you're not organized, get organized. I don't know how you're going to make it if you're not organized. Okay, so anyways, let's show. What do we have? M squared plus 1 equals 0 for. So M is plus or minus I. So 0 plus or minus I. So our complementary part will be C1 cosine x plus C2 sine x. Okay. Then I go to the original differential equation, do the, it's going to be d squared plus 1. And then for this part, if this was a solution to a differential equation, the roots would be m equals plus or minus 2i, and also m equals plus or minus 1i. Okay? So the annihilators, if you were to back engineer it, it's m squared equals 4, right? So -4. So m squared plus 4 is one of them. So I have d squared plus 4. And then the other one, it will be m squared equals -1. So m squared plus 1 is the other annihilator. So d squared plus 1. The solutions of that characteristic equation then are plus minus 1 plus minus I, plus minus 2i, and then plus minus I again. And that's where you see you have to go through this process. You can't just say, ooh, I only have 1 plus or minus I, because that was kind of part of I already have that part in the original differential equation. No, you're going to have a repeated root situation here. So in your solution to this part, what will the solution look like? It will be C1, cosine x plus c2 sine x. But because it's repeated, then you have c1x cosine x plus c2 x sine x. And then you have the other part. Oops, this should be c3, c4. Let's do that. And then plus c5 cosine 2x plus c6 sine of 2x. Okay. All right, so your particular part then, yp, I don't need this, I don't need this, I don't need, and then I need everything else. Wow. Really? Yeah, wow, that one's brutal. So I'll have ax cosine x plus bx sine x plus c cosine 2x plus d sine 2x. Oh. And then you can start taking derivatives and either go up to the second derivative. Okay, so the first derivative, on these guys you need product rules. Okay, so you'd have a cosine x plus, or it'd rather be minus because the derivative of cosine would be minus. So a cosine x, someday when my pen works, minus ax sine x plus b sine x plus bx cosine x plus, and then I need some chain rules on these guys. Cosine derivative is negative. So negative 2c sine 2x plus 2d cosine 2x. See if you can simplify that any bit. And I don't think I can, so I'm going to go to the y double prime with p, the particular solution, the second derivative of the particular solution. So the first guy, negative a sine x, and then this guy I need 2. The product rule would give me negative a sine x minus ax cosine x, then the next guy plus b cosine x, and then this one needs 2 derivatives, so minus bx sine x plus b cosine x, and then chain rules again, minus 4c cosine x minus 4d sine, oops, these are 2 x's, sine 2x, okay. Then I need to kind of plop them into my differential equation. In particular, I need to add this guy to this guy. Ooh, I should have simplified that guy first. Let's simplify this. I apologize. So it's negative 2a sine x minus ax cosine x plus 2b cosine x. Right, so there's 2 of those, and then there's just 1 of those, and then there's 2 of those, minus bx sine x, and then these 2 dudes, c cosine 2x minus 4d sine 2x, and then I can add those 2 together. Okay, so not this guy, but rather this guy, right? Because the differential equation wants y double prime plus y. Okay, so adding these guys together then, this dude, there's just 1 of those, so negative 2a sine x, and then negative ax cosine x will cancel with this, and then I have plus 2b cosine x, so this guy. Then the bx sine x and negative bx sine x will cancel. And then I can add these things together, so I get minus 3c cosine 2x. Adding these together, minus 3d sine 2x. And that'll equal 8 cosine 2x minus 4 sine x. And then I can start equating coefficients. So for the sine x on this side, where is my sine x over here? I'll have negative 2a equals negative 4. For the cosine 2x, cosine 2x, I'll have negative 3c equals 8, and then 2b will equal 0 because there's no cosine on the other side, and negative 3d will equal 0 because there's no sine 2x on the other side. Okay, so b is 0 and d is 0. Okay, a is going to be 2, c is going to be 8/3. So my solution is going to be y sub c, c1 cosine x plus c2 sine x. And then my particular solution, which is now somewhere way up there. Oh, I see it, it's circled. It's right here. So that's going to be ax, so plus 2x cosine x. And then b is 0, and then c, so plus 8/3 cosine 2x, and then everything else is 0. Let me see if I'm even on track. Okay, so yeah, I think so. I got that. See, you can see my particular part is correct. I just got to get the c1, c2 from the initial conditions. So my initial conditions, y of pi over 2 is -1. Y prime of pi over 2 is 0. Okay. So I need the derivative. So y prime is going to be negative c1 sine x plus c2 cosine x. I need a product rule on this. So plus 2 cosine x minus 2x sine x, and then product rule plus, or rather it would be minus because cosine looks like that. So minus 16/3 sine 2x. Okay. The first initial condition, plopping that into here, I would get -1 equals cosine of pi over 2 is 0, so that first guy is 0. Sine of pi over 2 is 1, so I would get c2. And then, again, cosine of pi over 2 is 0, so 2x cosine x is 0. And then 8/3, so plus 8/3. Cosine of 2 times pi over 2 is the same as cosine of pi. Cosine of pi is -1. Okay, so we get -1 equals c2 minus 8/3. So c2 equals -3/3 plus 8/3. So c2 equals 5/3. Okay, now plug the other initial condition into here, and you get 0 equals negative c1. Sine of pi over 2 is 1. Cosine of pi over 2 is 0, so the second part is 0. The third part then is also 0. And then the fourth part is going to be minus 2 times pi over 2. And then the sine of pi over 2 is 1. And then minus 16. Sine of 2 times pi over 2 is the sine of pi, and sine of pi is 0. Okay, so we get 0 equals negative c1 minus pi. In other words, c1 equals pi. And then I could write up my final solution. Y equals what the heck, c1? Pi cosine of x plus 5/3 sine of x plus 2x cosine of x plus 8/3 cosine of 2x, and then do a drum roll and hope you get it right, which I did not this time. 8, 9, 10, 11. Cosine, sine of pi over 2 is positive. And what happened? Sine of pi over 2 is positive 1, and then this would be 0, and then you'd have 8/3 times cosine. There it is, -1. All right, hold on. I see it. It's way back here, -8/3. So this would be -8/3 here. And then this would end up being positive. Sorry about that. starting to wish a calculator or a computer could do this for you. Yeah, you kind of see what they were up against in the early part of the century. They definitely wanted to program this in the computer so that people make mistakes. Computers don't, right? Anyways, plugging in then with the appropriate sign, plugging in pi over 2. Cosine of pi over 2, this first term is so going back to here. The first term will be 0. The second term, sine of pi over 2 is 1, so you just get C2. Third term, cosine of pi over 2 will make that 0. And then the fourth term, 2 times pi over 2 is pi. Cosine of pi is -1, but it's already negative, so you just end up with positive 8/3. So C2 is going to be negative 3/3 minus 8/3, which, so C2 is going to be negative 11/3. Plugging the other initial condition now into the second equation, you get 0 equals negative C1. The second term is 0, third term is 0, fourth term negative 2 times pi over 2, sine of pi over 2 is 1, and then the 16th, that ain't going to change anything, right? So you get C1 is equal to negative pi, and so I believe then our solution, y, is negative pi cosine x minus 11/3 sine x plus 2x cosine x minus 8/3 cosine 2x. Okay. Let's make sure it's right. Yeah. Okay, so these are very hard problems computationally. I mean, a computer can do this no problem. Human, not so easy. You're gonna have to make sure you're very organized, and so on and so forth. So this section and the next section are both computationally exhausting, in my opinion. So you're going to get a lot of work in there doing derivatives, just learning how to keep your work organized, and spending plenty of time wishing you could just have a computer do it for you, which will be good because that'll force you into computer programming, I hope. So anyways, I don't know. Anyways, thank you for watching, and I'll see you later. See you next time.